authorization, I'm going through the green card process, and when you're going through the green card process, you're in a travel ban, so I can't be there. So I apologize for that. And I have to say, I'm a little bit jealous seeing all my scientific friends hanging out there. It feels a little bit like when I was grounded and all my friends were um, in a party, and I was jealous about that. The difference is that this time, if I sneak out and try to sneak in, I will end up in jail, and then I wouldn't. I would prefer not to that thing not to happen. And yeah, that's very interesting talks. I've really been enjoying a lot the talks that I've been hearing, and I had a lot of questions too, but I couldn't speak through the mic, so I'll have to say the questions by the time we meet in person. In today's talk, I'm going to spend a few minutes telling you about different things that we have been doing in Medtronic related with multiphysics, hard modeling. Why do we need this type of modeling in the industry, and how in Medtronic we are leveraging this type of modeling. First, I want to start with an argument of why modeling alone won't solve anything. And in this plot over here, you're seeing a graph of the technical performance of a device with respect to the investment in time or money, right? So, and that plot that you see over there is a traditional approach. The more money or resources that you pour into a project, the higher the technical performance you get. And it's obviously an asymptote, because there is a point where you keep pouring money and you don't get anything back from it, right? So there is an efficiency threshold that we need to choose when we are developing devices to get the maximum performance possible for an appropriate cost for the device. The thing is that modeling can be considered a rapid prototyping technique, right? It's a fail-fast approach, like 3D printing or combinatorial chemistry or other type of models. So the working principle of these fast prototyping approaches is that you rely on some hypothesis that lets you run many iterations or many versions of the experiment at the same time. And the argument is that when you exploit this type of rapid prototyping techniques at the beginning of the R&D iterations, you get more of it, because the more information you have at the beginning of the design cycle, the easier it is to make the changes, right? So that's why this second curve is showing how the novel fail-fast approaches work, right? You have some hypotheses that let you run more experiments at a faster pace. The technical performance won't be the same, because you will have some hypotheses that are limiting your capabilities, but you're iterating much faster, right? So the secret sauce here is learning how to change. Learning how to change from the fail-fast approach to the traditional approach, right? So in that way, if you know the sweet spot, you can exploit these rapid prototyping techniques at the beginning and then change to the traditional approaches and end up either on a shorter timeline with less resources and even leaving a gap for innovation. Well, to summarize this slide, the advantage that we have in the rapid prototyping techniques as computational modeling is the exploitation of this massively parallel number of experiments you can do at the same time. To give another argument, I don't have to sell you this, but I like this slide over here. I'm showing a plot here of the fastest computer in the world on each year since the year 1993. The x-axis is years, and the y-axis is the flops of the computer, so how fast the computer is. It's a number of operations per unit you can do. But it's like, it's a logarithmic scale. But it's like hard to grasp. What is 100 trillion flop? What is 10 trillion flops? It's really hard to grasp that number, right? So just for have that in mind, the fastest computer in the world in the year 2003 was the Japanese Next Air Simulator. That computer had 35 teraflops. The price of that computer was $800 million. It consumed 3.2 million watts, and the electrical bill was $1.5 million a year. Today, you can get 35 teraflops with an iPhone 14 for $1,000. Just to keep the units consistent, an iPhone consumes 3 watts a year, and the electrical bill for charging an iPhone is $1 a year. So this is overwhelming evidence that 20 years from now we will have the fastest computer in the world today in our pockets. So this is the desired situation. This is what we want in the biomedical industry. We know what is the final user. The final user is the patient, and to have evidence to implant the device in the patient and to make this patient's life better, we need to show evidence to the regulatory agencies that their device is safe and effective. So the closest evidence to the patient is the clinical trials. The clinical trials are still a model. You're getting a group of patients, and you're assuming that a group of patients will behave like the final group of patients, right? This type of evidence is very costly per patient, and also it doesn't scale, so it has a lot of problems. So of course we try to use cheaper forms of evidence, like for example clinical trials. Those are still expensive, but they are a little bit more controlled. And then if you go a little a level below that, you can do bench experiments that are cheaper and they're more controlled, so you can handle more variables on that problem. And if you go to the bottom of the scales, where you're taking the more hypotheses, you have what I'm calling here the simulation trials, right? These are the cheapest types of evidence, and you have very controlled use conditions. It's a type of evidence that is embarrassingly parallel. You can run as many experiments as you want, as long as you have a large enough computer. And also another thing, that computers simulations can be run every hour of the day for every single day of the year. And also because of Moore's law, the slide that I showed before, you will have computers that are twice as fast every 2 years for half of the price. Now, as an experimentalist, to run twice as many experiments every 2 years for half of the price, that will never happen. The real situation actually looks something like this. We rely most of the evidence for the decision in the clinical trials. And the closer we go to the design loops, the less amount of this cheaper, fast type of evidence that we see. So what ends up happening a lot is that you get to the end of the process, to the clinical trial, and that you realize you need to go back to the design board, and that is very, very expensive. Okay, so now I'm going to show some applications that we have inside of Medtronic, where we have been using modeling. I need to look at my cheat sheet here because I didn't build the slide. This slide was built by Kevin Sack. Some of the applications we have done in Medtronic is we have used hard modeling to explore how fast pacing can be used to help patients with HFpEF. The hypothesis is that if you start beating the heart faster, it relieves HFpEF. These simulations results are being compared with actually clinical trials today. So we have also been using modeling to understand the capture threshold for pacemaker leads in virtual cohorts that are also being compared with clinical trials. This is another project, and this project we have been trying to optimize an ECG belt that goes around the chest and the position of the leads to create better metrics. So the question is where the leads should be and where the separation of the leads to maximize the information you get from that belt. Another very interesting experiment is the sensitivity of the Micra. Micra is one of the pacemakers we commercialize in Medtronic. what is the sensitivity of the location of the pacemaker, because you can imagine this is a very complex mechanical system. You have a pacemaker inside of a heart that is deforming, and also the pacemaker has a mass, so it doesn't move directly correlated with the muscle. Also, we are replicating clinical protocols that are demonstrating the efficacy of anti-tachycardia pacing algorithms. And finally, something else that the group at CRM has been doing is studying the sensitivity of different defibrillation thresholds for external for defibrillators that are located outside of the chest, under the skin. And now I'm going to make a little example. I'm going to show in some more detail one of the models that we have at Medtronic. So we call this a three-physics model. So we have the electrophysiology that is being bidirectionally coupled with the solid mechanics, and that solid mechanics is coupled also with the fluid dynamics. So what we can do basically is replicate the different signals that we can extract from the heart, right? In this case, this model is based on LS-DYNA, and you can turn on or off different blocks depending on the problem that you're trying to solve. Well, here I'm just like showing some eye candy. What you can see here is a long axis cut of the myocardium, and you can see, I'm not showing the electrophysiology here, but you can see how the muscle contracts and how the muscle is pushing the blood out of the chambers. You have different other cuts in the top right corner. This is another application where we deployed a lead inside of the ventricle. The application here is to measure the change of the radius of the lead, because that's correlated with fracture. And this is one example of something that is in the near term, where we plan to deploy a device, digitalize the entire design pipeline to make that a loop and optimize that. So you can imagine how every step of the production of in this case, a heart valve can be digitalized, right? From the creation of the pattern that is going to be laser cut in the nitinol cylinder, to the annealing of that frame and the crimping of that frame in the delivery system. Afterwards, the positioning of the frame in the aortic sinus, and the deployment, and of course the fluid-structure interaction between the leaflets and the fluid, right? If you have a pipeline like this, you can think of deploying a pipeline in a database like the Cristobal or the Marina database. These are human hearts, so we can think of deploying this automatic framework fabrication in this set of hearts, and you can think of having something like this. The human hearts can be characterized with probability distributions, right? So you have a set of uncertainty parameters that are in the human heart, right? And there are some variables of the system that stand deployed in the heart that you can control. For example, if you think about the coronary valve, you can think about the strut width of the strut height, or the leaflet thickness, things like that. So you can automatically deploy these frames in the heart, and you can extract the same measurements that you would extract from a clinical trial. The thing is that in this case, everything is structured and standardized. So now it's really easy to extract the statistical measurements from these virtual experiments. And after that, as it is a computer system, you can create a loop. So you can create a case called optimization under uncertainty. You can create the best frame design for that uncertain population. So to finalize, I just want to summarize a few ideas of the slides. First of all, the biomedical industry will transform in the same way the automotive and the aerospace industry did 30 years ago. We only are behind that schedule because we have a very strict regulatory environment. Also, this type of massive parallel experiments is what allows us to exploit the modeling and simulation in the early R&D cycles. And these physical database models are delivering an unprecedented throughput that can be used to make quick decisions at the beginning of the iterations. And yeah, and the final idea is that, I mean, simulation alone is not going to be as powerful as combining simulations with the classicals for sources of evidence. And I would like to finish my talk with a message. I started saying how you have to combine simulations and experiments to get something better. And this is something that you can also see in this sport in Catalonia called Castells. You can think you cannot only build a structure like this, something that is amazing with just one set of skills. You need to always combine different sets of skills. So in the structure like this, you see very strong, sturdy people in the bottom of the castle that are holding the weight, but you also need a very skilled with fine motor skills, kids that are climbing up the tower without throwing it down. So that's everything for today. And if there is any questions, I'm obviously open to answer them. I hope I'm not very over my time. Thank you so much.
Thank you, Alfonso. Can you hear us, by the way?
Yes, I can.
Excellent. Are there any questions from the audience? Maybe I'll just ask a quick question. Is there any part of Medtronic where modeling isn't being used that you think it should be being used?
Yeah. So it's actually the other way around. So the parts where we are actually exploiting modeling are just a few in Medtronic, and what we're trying to do is expand the use of modeling to more areas or operational units. It's not an easy task because we have been doing the things the same way for 70 years, and this is the way that works, that we have evidence that works. So changing or making an investment to use a new form of evidence is like it's a struggle, but we taking baby steps, we are getting there.
Thank you. If there's no other one quick question from Steve.
I was wondering, Alfonso, if you thought that the priority for Medtronic was to look at simulations of animal models to replace the preclinical studies and accelerate those, or do you think it's more important to just go straight to patients? Like, I can see there's two different priorities.
So, sorry, the sound is not great. So your question is if we are planning to do simulations of animal models or human like models?
Is there a priority between the two?
It's a good question. Okay, if I have to bet, I would say that human models are preferred when we show models based on animal geometries. The answer back is generally, oh, cool, when you're going to do the human. So at the end, a model is applying some hypothesis to the system that you want to represent. In this case, the final system, the ultimate system is the patient, the human patient. So I would say that human models are preferred over animal models.
Thank you very much, Alfonso. Thank you for keeping.
Yeah, thank you all, of course.
Thank you.